Good morning, everyone. Today I'm going to introduce my research, solar irradiance estimation and prediction based on whole sky image. My name is Gao Shuo, and my advisor is Yi Guangyu. Here are my outlines. First, I would like to introduce my motivation and research background, database and system structure, and then it's our proposed methods. They include solar position algorithm, red-blue method, optical flow, and LSTM model. We apply in this research. Third, we are going to show you about our experiment results. Finally, is the conclusion and future work and reference. And first one is the background and motivation. Solar energy is the main part of development of renewable energy, but solar power generation is easily affected by the environment, including the influence of factors such as solar zenith angle, solar shading, and components. In particular, cloud occlusion has the greatest impact on solar irradiance prediction, as shown in the following two figures. When the sky is clear and cloudless, you can get a stable amount of solar irradiance. But if there are clouds covering the sun, the amount of solar irradiance will be greatly affected. Such problem will make the solar power generation unstable and affect the power grid, give a loading pressure. And in this article, the all-sky image used is from the National Renewable Energy Laboratory in Colorado, USA. The all-sky image and solar irradiance data collected by the all-sky imager TSI-16 and CMP-22. The feature of the all-sky image is to present a complete sky range in image and has elements such as water vapor and color reflected by the sun, clouds, and atmosphere in the sky allows us to get the information in the entering sky. The image is at an interval of 10 minutes, 10 January to March 2018. And then, firstly, the structure of the solar irradiance estimation system. There are the three kind of input parts: the global weight and the regional weight, and extracted from the all-sky image. The global weight includes cloud ratio and cloud thickness in the sky image, and the regional weight of 10 after performing local partial cloud feature extraction. Finally, consider the time and use the LSTM model to train the amount of the solar irradiance. Then, this is the structure of solar irradiance prediction system. The difference from estimation is that the local part, optical flow method, is used to generate the predict cloud shadow map at the next moment, and the regional weight is extracted from it. As the irradiance estimation result calculated by the previous structure. And finally, then use LSTM to train the prediction model. And then this is the first proposed method, solar position algorithm. In the sky image, the problem of unknown curvature of the dense surface must be considered, and the coordinate of the sun center cannot be obtained directly by calculating the sun elevation angle. Therefore, we apply that propagation network is an optimal way to train the sun center position using this algorithm. The evolution algorithm belong to semi-supervised learning method, which give the training feature as input and the correct result as output. Through the concept of gradient descent, the cost function is minimized to obtain the result with the smallest error. By using the backward transfer neural network, the calculated sound altitude and altitude are used as input feature, and the sound coordinate of the observed image are used as output for condensing to correct actual sound position in the image. Figure 6 shows the result of training solar sensors through big backpropagation network in general, where the red mark the observed sound coordinate. The blue lines are the altitude angles and altitude angles calculated from the time, longitude and latitude. And the black line are the condensation, the result of test. Through this method, the position of sound in the image at different times can be found. And the second one is the red-blue ratio method. It is a method to identify clouds. Since the clear skies usually scatter more blue light than red light, the sky and cloud can be classified well by comparing the red-blue ratio, RB fixed in the RGB space of sky image. However, its disadvantage is that it cannot show the thickness of cloud, and the picture is cropped solar area. So this study used an improved method, red-blue ratio method, RBSV. Divide RBSV by Y. Y is the brightness of the image, and take this method can present the thickness of cloud. Finally, if the sun is not blocked, the minimum value should be taken. Therefore, we set up a Y more than 0.9 is regarded as the sun area, and change the cloud pixel to 0, and the final result is shown in the RBSV on the right. And in the goal weight input, a threshold value alpha will be set up to judge whether the pixel is cloud after the 5 red-blue ratio method of this whole sky image. If it is greater than 1.3, it will be judged as a cloud. These judged results are presented by binarization of cloud distribution result, C distribution. The cloud ratio is to calculate how many proportion of entire image determined to be cloud, and the cloud thickness is to calculate the average value of these pixels are cloud. And in linear way, the center of sound is obtained through the solar position algorithm, and then the area of the center, the sun click to remove the sun using Y more than 0.9 as the judge. And the distance between the cloud and the sun is considered by using inverse distance weighting. And finally, this value cut into 16 pieces as original input, as the figure 11 shows. And then is the forecast system we will use the optical flow, and I will introduce the optical flow method, which is a method to detect object motion. Generally, optical flow has two basic assumptions. One is brightness consistency. That is the brightness of two near frames. The grayscale value remains unchanged, and the spatial coherence. That is, the movement of near pixel of object is continuous. In this way, the moving vector of the object is consecutive frame image pixel-wise is calculated. Lucas kinetic optical flow method is a most common way. It adds the assumption that motion direction of near pixels of an object is constant. That is, in window center on target pixel, all pixels have the same optical flow vector UMV through the optical flow. The movement of cloud from the previous frame to current frame is average. Then the motion vector UMV is obtained by using the least square method. And here is an example we will use to demonstrate the application of LK optical flow method. The first input is Oscar image at moment t minus 1. Before and then is input is the Oscar image at time t. And by the optical flow calculated by LK assumption is shown as the yellow arrow, with the sun as the target window, and the surrounding pixels all have the same optical flow vector UMV. Assumption that cloud velocity remains constant. Through the batch project method, make cloud image at time t plus 1, and then extract feature weight value from this predicted image. And then it's the model we use to predict and estimate the solar irradiance. In this part, we take generally for example, this is the LSTM model parameter I use to train the estimation and forecasting. There are 2,144 images, and 80% we use to training and 20% we use to testing. And then is the performance index we use to evaluate the result of training. The R square is reflect the fitting effect of model, and mean square error compute the mean absolute error between the true and predict, and the root mean square error highlight the impact of abnormal value. And here is the experiment and result. At the figure 15, MA and RMSE is gradually increased at a longer forecasting time, and R squared is gradually decreased. And then is the one-step actual and predict comparison in January. The blue line is real solar irradiance, and orange line is the predict result. The next one is the two-step. And then is the three-step actual and predict comparison in the January. And then is the conclusion and future work. These different image feature values are used as the input in a STM model. The learning events have been predicted, and future work add more parameters for weather classification. And under different weather conditions, cloud movement also has different states. We have to consider this situation. And here is my reference. Thank you for attention.
So may I have some questions from the audience?
you extract the picture on image. What its physical picture is? We use the regulation method to segment the cloud from the sky and use the white brightness function to calculate the cloud thickness.
So may I have one more questions from the floor? No?
Why do you use regional weight as a feature?
Due to the cloud occlusion nearby the sun causing a great impact to the earrings. We use regional way to extract cloud more carefully.
Thank you.
Okay. So any other questions from the floor? Okay, if no questions, I think we can invite the next presenter. Thank you for your presentation. Next presenter is Chen Wilson.
Hi everyone, my name is Chen Bosen and my adventure is Huang Zhenji. My title is Fairness and Low Bands in 5G millimeter wave using as control. It is my title. First, I will introduce 5G millimeter wave background, and then I will talk about fairness allocation. Final is a map simulation. 5G is the attention of the 4G technology with performance include high data rate, reduce latency, energy saving, cost reduce, increase system capacity, and connectivity for large deployment to get a better network experience. In this speed, we can see 5G is faster than 4G. The disadvantage of 5G, the signal fades quickly. It means more base stations need to be built. For the 5G millimeter wave, advantage is the highest speed, a large capacity, and low latency. According to this paper, Wi-Fi is considered as 5G small base station. From the image, it can be seen that the area marked in red have a very small range. There are two competitions for this paper. First is the faster the user moves with, the better the performance of the connection strategy for that user. The second is the more then the low, the better the performance of the connection strategy for that user. And in this case, the x-axis means the distance from the transistor to the receiver, which the y-axis means the probability of line connection. P loss is the probability of line of sight wave, and Pn loss means probability of line of sight wave, and P dot is the probability of disconnection. According to this figure, when the distance between T star and R star more than 200 meters, the probability of disconnection is 100%. Next, I will introduce max mini fairness allocation. First, I will talk. Conclusion is without affecting user who often maximum resource. Allocating additional resource to users with minimum resource can help reduce the gap between the users. The code is divided into 3 steps. First, use LP1 to find a load group Y, and then use Y from LP1 to find the load AP and user. Third is remove that load group. It means remove all the user and APs in that load group to find a new load group. This argument uses linear programming to find a optimal solution. After remove that optimal solution, it iteratively find the next best solution and remove it until it cannot be removed anymore. And this is a paper example. There are 3 AP, APA, APB, and APC, and there are 5 users, user 1 to user 5. And in this figure A, its data indicates all the possible combinations with the numbers on the line, representing the combination rate. The APA is connected to the user 1 with a combination rate of 1. The APB is connected to the user 4 and 5 with combination rate of 2 each. APC is combination to user 2 and user 3 with combination rate of 2. And C APA is connected to the user 1 with a combination rate of 1. The APB is connected to user 2 and user 3 with combination rate of 4. And APC is connected to user 4 and user 5 with a combination rate of 2 each. And for big D, APA is connected to the user 1 with a combination rate of 1. And APB is connected to the user 2 and 3 with combination rate of 4 each. And at the same time to user 4 for 1 divided by 2 of the time. And connect rate of 2. And APC is connected to user 5 with the combination rate of 2. And at the same time to user 4 for 1 divided by 2 of the time, connect rate of 2. According to big B, A1 divided by 1 means APA connections to user 1 are divided by rate. Rate is 1. And for B, 4 divided by 2 means APA connected to the user 4 are divided by rate. Rate is 2. And according to those answers, can find NBV. NBV is a normalized bandwidth vector, and it means high lexicographical value. High lexicographical value means high to low. According to NBV, we can find the low vector. And I will talk about the Maiden simulation. First, I use its sensitive mode. That's all possible combinations according to algorithm LP1 in a matrix. A11 is the first user connected to the APA, and A24 is the second user connected to the APB, and equals 0.5 means inverse of rate. And then I will find the answer according to the reason of LP1 in matrix dash S. One represents is a possible connect when 0 represents no connect. Mini dash S dash I mini dash S dash I correspond to the AP and user. Mini equals minimums of the maximum load vector. can use the Y to find the LPY. Make sure the correct load books. And the reason of the LP2 can find YA equals 1, and YB equals 0.5, and YC equals 1. Each AP can generate at most one load grade. In this example, with 3 APs, there have been a maximum of 3 load groups. According to the reason, LP2 YA is 1 and YB is 0.5 and YC is 1. So LP2 can find that YN equals YC equals 1, but since user board can connect with both YB and YB at the same time, the load 1 YC can be reduced and transferred to YB. In German, YA can be the load group, and in the new interrupt, YA will be removed. Remove the load groups of the YA, which include APA and user 1. Leave between 2 AP and 4 users, which can form 6,11 matrix. The remaining groups will become a fairness group. It cannot be removed anymore because all the load vector is 0.5. So in the red one is my main simulation result. It has same value with paper. After that, I will use a large sample to verify that my algorithm has no problem in my master paper. Now this is my reference. Thank you for listening.
Thank you for your presentation. So, any questions on the floor? Okay, frankly speaking, I'm not one. Frankly speaking, I'm not one in the field, but after your presentation, I knew you try to use min-max or max-min allocation, right, to reduce the gap between the users, right? Yes. This is your main objective of the research, but it is still unclear to me what the research gap are you managing to close out. Yeah. Because you didn't show me like a state of art techniques and then what is problem statement, yeah. Huh? I mean, 因为你是就是做研究，做研究的理论上的话，这个并不是你第一个去解决这个问题，所以理论上应该现在有蛮多其他的研究相关的东西。可是问题是，我知道你用那个方法去做这个东西，但是我不晓得现在的技术的瓶颈在哪里，解决了什么事情。
基于好美国应用现在还没有，就是市面上还没有这些东西，所以这只是假设有这些问题，然后去做。
假设有这些问题，就是说没有做过这个问题。
因为我觉得就是我怕它的范围太小了，只有200公尺，那就是市面上我们现在的网络都是4G 或者是4G 少，就是不是那么不是毫米波的5G，所以目前还没有遇到就是这种分配性的问题，这只是假设有就是这个问题，然后我们尝试解决这样。
Okay, so you assume there's a problem, and then you are the first one to try to
它的连线距离会比较远，它可以就是它不像5G好很多，它而且因为毫米波它的波长比较短，所以它的传感性很差，所以中间会有一些
Okay. So the problems you mentioned, this one is assumed by you.
所以但是我用之前的就是解决 WiFi 的方式，然后应用
And
在
then are you the first ones who solve this problem?
就是算是不同的，但是应该是同一个方法。是用的对象不一样，但是是类似的。
So which means you follow the ideas from other applications to this field and to solve this problem. Am I right? So any questions from the floor? Okay. So if no question, thank you for your presentation. Let's welcome the next presenter, Wang Yong.
Okay. Hi everyone, my name is Yongming Wang and my advisor is Weiyan Wang. Today I'm glad to present my research on the lightweight network architecture for human posture recognition. And first, I'll begin with the introduction. In discussing the reasons behind our research and explaining how we do it. Next, I will introduce our system architecture. Then we will talk about the early neural network. After that, we'll introduce the much early neural network. Furthermore, we will present the results and the conclusion. Okay. And in recent years, with the proliferation of artificial intelligence and computer vision technologies, human pose recognition has garnered significant attention due to its wide range of applications, including human computer interaction, surveillance, and healthcare. The accurate identification and tracking of human poses from images or videos have become crucial tasks in various domains. The task of human pose recognition is typically divided into two steps. One is the extraction of human features, and the other is the classification based on these features. And for feature extraction tasks, some papers utilize the human pose estimation algorithm to gather skeleton data, like OpenPose and MediaKite. And some utilize the object detection algorithm, like Max-Gaussian, to gather pixel data. And the method we choose for the feature extraction is the human pose estimation algorithm. This is because compared to pixel level image features, skeleton features typically have lower dimensions, leading to higher computational efficiency. It accelerates both feature extraction and subsequent the classification processing. And it accelerates additionally, skeleton feature extraction methods generally exhibit certain accuracy in human pose recognition under different viewing angles and lighting conditions. Hence, we choose the human pose estimation algorithm, DW-Pose, for feature extraction. And in the text of posture classification, some papers utilize the convolutional neural network for classification. However, convolutional neural networks typically require a large amount of training data, making it difficult to create a training data set. Some utilize like ResNet for classification, which has good accuracy but suffers from slow computational speed due to its large network size. And for these reasons, we utilize much fuzzy neural network as the classification method. The much fuzzy neural network not only offers fast computational speed but also achieves good training results on small data sets. And here's the system architecture. First, the
Then the data set is sent to our network. The scores of each pulse are displayed. And the main concepts of human pulse estimation can be divided into two steps, two types. And one is the top-down. The top-down approach will use the object detection algorithm to get the locations of humans and use the bounding box of the location to search the human key points. And second is the bottom-up. Bottom-up approach will find all the key points in the brain and connect them to form the skeleton of the human. Generally, the top-down approach tends to be more accurate but time-consuming, while the bottom-up approach is faster but may sacrifice some accuracy. We want a high accuracy to prevent a misjudgment of the skeleton itself. Hence, we choose the beaten pulse as our method. And first, before we talk about the much further neural network, let's discuss the body neural network. A body neural network, also known as the body neural system, is a computational model that integrates body logic with artificial neural networks. It combines the capability of body logic to handle uncertainty and impression by the learning ability and pattern recognition capabilities of neural networks. In a body neural network, the process begins with verification using membership functions to represent input data in body sets, and subsequently, a body role base is established to capture the relationships between inputs and outputs. Next, body inference is performed to derive body outputs based on this rule. Finally, the verification is applied to convert body outputs into crisp results. And due to the large number of weight parameters generated when the number of input variables increases in traditional body neural networks, it consumes a lot of computational time and may even cause computational problems for users. Therefore, the merged body neural network is a solution that's designed to address this issue. It achieves a hierarchical learning architecture by splitting into several body tasks before verification. By merging 6 inputs in one body block, we can reduce the parameters in raw layer from 3 to the 36 power into 3 to the 6 power times. And the inputs for our merged body neural network are the human key points from the DW pulse. The DW pulse will return 18 key points. We use 2 identical sets of these key points of the merged body neural network. We merge the two identical inputs in a different way. The way we combine is shown below. As we discussed, by adding 1 identical set of key points but merge them in a different way, we can compress the rules, make its diversity better. We also add 1 batch normalization layer after the raw layer to expedite the training process. And this paper proposes a novel human posture recognition by integrating the Eden pulse model with merged body neural network. The proposed method enables effective posture recognition even with small data sets. The preliminary experimental results demonstrate our proposed method achieves significant advantage in both accuracy and faster training convergence aspects. This figure is shown that our method compared to the original merged body. And here's the reference. And here's some data set and neural network setting. Okay, thanks for your listening.
Thank you for your presentation. Any questions from the floor?
for presentation. So interesting subject. I think it's pretty cool, but the problem I see in your presentation is you forget to compare yourself to other algorithms in the results and also in the weight of the network. So could you like give us some insights about this? Like what gains do you have? What is the number of parameters of your network compared to like OpenPose? And what is the accuracy compared to OpenPose? And what is the FPS gain that you have? This is kind of important if you want to publish this.
Sorry, but you want to me introduce like PWPost and OpenPost difference or what? I'm sorry, but I'm very confused.
Not really. It's more like when you do this kind of presentation, don't forget to like compare yourself to the state of the art. Because right now your algorithm is working. It's pretty cool. I don't say it's bad, but you have to say, oh, it's better or it's worse, or what is the comparison between this and OpenPose. Because now, for example, in our lab, we will use OpenPose for future projects. And why would I choose your project instead of OpenPose? You have to compare. You know what I mean?
Okay. I'm very sorry about that.
No, it's okay.
And I think I don't explain this very clear. OpenPost is the human post estimation method, but what I do is human post recognition method. That's different. And I use the PWPost is very similar like the OpenPost. It will let me capture the skeleton data, and I will use this skeleton data to do the classification, and I can use this to do the post recognition, not estimation. It's different.
Okay, I see. But in any case, you still have to compare yourself to something, right? To the state of the art.
I compare to someone use the multiple neural network to do the classification, but I do some modify in the polynomial network. So in multiple neural network, sorry. Yes. And by adding some another set and merge them in different ways, so I can get a higher performance than the previous method.
So the state of the art before can only get 60% accuracy? I don't think so.
Yes, I'm sorry about that, but if I train it in 1,000 approach, like 1,000, and he can get maybe the same accuracy in my method, right?
Okay, so you have much faster
I
training.
can pass the training time.
Okay, okay. Okay, nice. Thank you.
So any questions from the floor? Okay, so no questions. Zhang Yingchen.张一晨有在吗？哦，对。
Hello everyone. Today I'm going to introduce 19 gigahertz phase shifter. And my name is Zhang Yingchen. My professor is Taizhen Han. This is our outline. We will introduce the background and the topology of phase shifters first. Then we will illustrate the circuit design and the measurement. At the end, we will have conclusions of phase shifters. Recently, satellite communication is getting more attention for high data rate transmission. Many commercial groups utilize frequency band around K-band to provide wide bandwidth. The uplink is set as 28 to 30 GHz, and the downlink is set as 18 to 20 GHz for high-speed internet. In tradition, the satellite communication, in traditional, the satellite communication system is using dish antenna to overcome the long distance channel loss. But the dish antenna is unportable and not easy to integrate with the planar circuit. So nowadays, people trying to develop phase array system with pitch antenna to deal with the portability problem and integration. This is the architecture of phase array system. It includes converters, mixer, phase shifter, and amplifiers. In the phase array system, the transmitting terminal controls the phase delay by the phase shifter, and the beamforming can increase the efficiency of wireless transceiver. The transmitting terminal can change the phase antenna set. It can enhance the signal strength of specific direction and inhibit the signal of undesired direction. It can also decrease the interference of other signals. And the receiver can accept the specific direction signal by phase array, and it can reduce the noise. In this link, there are amplifiers that cause large power consumption. We need a lower power consumption phase shifter to decrease overall power consumption possibility. As stated in the preface, we need to design a small size chip to have enough space putting the element into the phase array system. Because phase shifter back-end components are amplified, we need to design a low power consumption phase shifter to decrease the power consumption of the phase array as much as possible. To avoid increasing the complexity of the control system, we need a digital control phase shifter to help us simplify the control system. There are 4 types of phase shifter. The first is transmission line type. It includes pi type and T type. The pi type generates phase shift via adjusting the variable capacitor. The capacitor is sensitive as CMOS process, and it causes process variation. So that will cause the phase distortion. Therefore, in most cases, T-type is selected to achieve the phase shift. The second is switching type. It uses the transistor switch to simplify the phase control mechanism. It is also a topology having inherent digital phase control mechanism. The third is reflection type. There are variable capacitor in the load. It can change the capacitance through adjusting the voltage, so that the load impedance and phase will change. It can provide continuous phase shift, but it needs to integrate with high resolution digital to analog converter. The last is vector sound phase shifter. When designing, it must notice on maintaining precise phase and low power consumption. The table shows the pros and cons of 4 topologies for phase shifters. First is transmission line type. It is stable at any time because it only composed by transmission lines. but it has the degeneration of insertion loss. The second is switching type. It is passive circuit, and the phase shift can be controlled by simplified digital controlling switch, but it has high insertion loss and easy has phase deviation due to the process variation of the capacitor. The third is reflection type. It is analog control and it has smaller chip area, but when the area raises, the loss raises too. The last is vector sum type. It has better phase convolution and accurate phase shift, but it has bigger chip area and power consumption. According to our design consideration, we need a small chip size, low power consumption, and digital control phase shifter. So this time we choose switching type because of its intrinsic digital phase control mechanism, zero power consumption, and its better dynamic range. So the topology is easy for implementation. This paper shows bridge T type and 90-degree 4-bit phase shifters and high pass low pass network for 180 degree. It has great RMS amplitude error in the bandwidth, but the chip size is slightly bigger. Although using transmission line based bridge T type in this paper, the RMS phase error still doesn't get a better performance. And this paper shows the reverse direction phase computation technology. It's using to make the resource closer to the design goal. And this paper also shows the bridge T type and 90-degree 4-bit phase shift and high pass low pass network for 180 degree. Although getting a better RMS amplitude error than previous paper, the RMS phase error is higher and the chip area is more bigger. The switching type phase shifter has digital control mechanics, and it can change the reflection load by selecting voltage to let the 5 bits having the phase shift state and the reference state in order to have a compact chip area and minimizing the influence caused by process variation. Some of the inductors of the phase shifter are placed to microstrip light on CMOS process. The reason why small phase shift bits are in the middle of the topology is that the 3 bits easily have mismatch and loading effect. So they are arranged in the middle to estimate the loading effect and achieve high phase linearity. All the transistors here are body source connect in order to achieve the minimum insertion loss. Compared with the traditional capacitor-based bridge T-type topology for STPS design, the topology is insensitive and the transmission line has better modeling than capacitor. And the capacitors are the parasitic capacitance of the transistors at pinch-off region. When control voltage equals to 1.8 volts, the circuit is equivalent to the upper. It becomes a low-pass circuit, and it provides the desired phase shift. When the control voltage equals to 0 volts, the equivalent circuit on the below becomes a bandpass circuit, and it provides 0 phase shift. When designing switching T-type phase shift bits, we can calculate the ideal capacitance and inductance according to the equivalent circuit. After getting the ideal capacitance and inductance, we can analyze the most equivalent in capacitance to decide the size of the MOS. The left figure is the simulated phase difference of 3 bits from 15 to 24 gigahertz. We can find out that the phase performance of all 3 bits are close to their goal phase. The right figure is the simulated amplitude error of 3 bits from 15 to 23 gigahertz. All 3 bits at the main frequency are almost 0 dB. This bit is composed by coupler and sent to variable reflection load. In order to increase the output phase shift, we series inductor at the source of the transistor to change the imaginary part of the variable reflection load impedance. Due to keep the balance on the loads between the between the reference state and the phase shift state, we shunt the resistor to increase the loads at the control voltage. Because it needs a transmission line to connect the capacitor and resistor at actual layout, we add the transmission line to simulate in order to make the simulation more accurate. The left figure is the simulated phase between, the left figure is the simulated phase difference of bridge T-type and biphase switching reflection type from 15 to 23 gigahertz. We can find out that the phase performance of switching reflection type is more flat than bridge T-type. The right figure is the simulated amplitude error of bridge T-type and switching reflection type from 15 to 23 gigahertz. We can find out that the amplitude error of switching reflection type is more flat than bridge T-type too. So we choose switching reflection type for our 90-degree phase shift bit. There are 3 types of 180 degrees phase shift bit: double 90-degree switching bridge T-type and high pass low pass network, and also the biphase switching reflection type. This bit is composed by coupler and sent to variable reflection load. And it can change a variable reflection load impedance by selecting the transistor's bias to achieve the phase shift. In order to increase the output phase shift, we series inductor as the source of the transistor to change the imaginary part of variable reflection load impedance. Due to keep balance on the due to keep balance on the reference states and phase shift states loss, we shunt resist to increase the loss at the control voltage so that it can strike a balance. There has a shunt resistor at the drain of the transistor, so we simulate the circuit with and without this shunt resistor to observe the difference. The left figure is the simulated insertion loss of the bit. We can find out the insertion loss of the transistor with shunt resistor is closer between offset and onset. It means that there is a balance between reference states and phase shift states. And the right figure is the simulated phase difference of the 180 degree. So the result is that adding shunt resistor at the drain of the transistor can decrease the amplitude difference between reference states and phase shift states. A K-band phase shifter using 90-degree biphase switching reflection type is fabricated on 180 nanometer CMOS process, and the 180 degrees and 90 degrees phase shift bits composed by biphase switching reflection type, and the other 3 bits composed by bridge T type. The left figure shows the simulate and the measured relative phase shift of the main phase shift states from 15 to 24 GHz. We can find out that the measurements are all very close to the simulation, especially at the main frequency. The right figure shows the measured phase of all 32 states, and the phase shifter provides 32 phase states from 0 to 360 degrees. And the left figure shows the measured input return loss of 32 states from 15 to 24 GHz. And the right figure shows the measurement output return loss at all 32 states. And the left figure shows the measured insertion loss of 32 states from 15 to 24 GHz. And the right figure shows the RMS phase error and RMS amplitude error from 15 to 24 GHz. The RMS phase error at main frequency is 1.67 degree, and the RMS amplitude error at main frequency is 1.38 dB. This table summarizes the performance of recently reported phase shifter around K-band. These 5 digital bit switching type phase shifter provides 360 degree phase shift with resolution of 11.25 degree. Because this phase shifter is passive circuit, so the power consumption is 0, and the lowest RMS phase error is 1.68 at 19 GHz. The RMS amplitude error is 1.38 dB, and the chip size is 0.42 millimeters square. This phase shifter achieves better RMS error and the chip size. This 19 GHz passive phase shifter is implemented on 0.18 micrometer CMOS process. We use bridge T type and the biphase switching reflection type to achieve 0 power consumption and lower phase error. This design with digital phase control mechanic achieve lower RMS phase error and RMS amplitude error. And these are my reference. Thanks for your listening.
Thank you for your presentation. After your presentation, I realized you are managing to design a circuit with compact size, low power consumption, and the low RMS error, right?
Yes.
And then you starting with introducing the 4 type of topologies, if I'm not mistaken. And then you choose the switching reflection topology, right? As it due to its characteristic of the pass passive circuit and zero power consumption. Right. Then, yeah, I know you finished everything and you try to do a simulation and you measure it to do a comparison. Would you please tell me what is the limitations of your design circuit? This is question number one. And then question number two will be like, is it any suggested frequency range for using your circuit? Is it 13 to 23 gigahertz or what? I don't know.
And for question number two, my circuit is provided to
So suggested range
17 to 21 gigahertz is a better. It's a better
17
bandwidth.
to 21.
Yes, it's a better bandwidth.
Or because of the amplitude error.
Yes, and the RMS phase error.
Okay. And then for the first one, what is the limitations?
Because the circuit has the bandwidth limitation, so we only define in this bandwidth for the downlink.
I don't understand, sorry. Would you please rephrase it or explain this more details? So you mean that there's a bandwidth limitation?
Yes, because as a satellite communication system, we look at the downlink bandwidth limitation is 18 to 20 gigahertz. So
18 to
yes, yes, and our circuit will put at the downlink. Yes,
And then you said the suggested range is 17?
17 to 21 gigahertz.
Oh,
So it can cover the downlink bandwidth.
okay, thank you. Any questions? Okay, so thank you. If no questions, let's welcome the last presenter. Liao Xuanyi.
event detection system with full body posture recognition. My name is Xuan Liao, and my advisor is Wei-Yen Wang. This is my outline. I will begin with an introduction to the topic of my presentation. Following the introduction, I will provide an overview of OpenPOS, a popular library for human pose estimation. Subsequently, I will compare lightweight OpenPOS with OpenPOS, explaining the reason why I chose lightweight OpenPOS for my model. Moving forward, I will present my flow chart, describe the data representing date, and explain the methodology used in my research. Next, I will showcase the training dataset and the test dataset, and I will provide a demonstration of three kinds of poses along with their corresponding component scores. Lastly, I will showcase the test accuracy result and present my conclusion. In recent years, the integration of computer vision and machine learning techniques has paved the way for innovative solutions in various domains, ranging from surveillance to healthcare. Among these, abnormal event detection stands out as a crucial area of research, particularly in ensuring public safety and security. This paper aims to address the fundamental issue by developing an abnormal event detection system for factory scenes. The proposed system mainly captures human skeletal information and then utilizes a proper simplified multi-layer perceptron network to identify various human portraits, including fall, squat, kneel, stand, and sit. OpenPOS is a real-time system for body, foot, hand, and facial key point detection, and it is being widely used today for many research topics. Figure 1 is the pipeline of OpenPOS. In Figure A, we input the image, followed by the simultaneous prediction of confidence maps and part affinity fields vectors by the model. Subsequently, post-processing is applied to the prediction from the second step, resulting in the overall pose. Let's first take a look at the model of OpenPOS. The model iteratively improves the accuracy of predict joints and slings through multiple stages. In the figure, S represents the input of the first stage, which consists of image features extracted after placing the image through the first 10 layers of the VGG19 model. These image features are then fed into two sets of CNN, as depicted in Figure 2, Branch 1 and Branch 2. Branch 1 predicts confidence maps for each key point, where each key point corresponds to one output feature map. For instance, if there are J key points, it will generate J feature maps. Branch 2, on the other hand, focuses on each link and defines a new concept called PAL. Each link is represented by a 2D vector. If there are C links, it will generate C feature maps. The above two branches can respectively be expressed by the following two equations, ST and LT, where ST represents the confidence map predict for each key point in the T stage, and rho denotes the CNN architecture of the T stage. It is worth noting that the architecture of the first stage differs slightly from the subsequent stages. The input of the first stage includes only features extracted from the 10th layer of VGG, and its internal CNN architecture consists of only 5 layers. From the second stage onwards, the CNN architecture comprises 7 layers. In addition to the featured effect from VGG19, the input of each subsequent stage also calculates the convergence map generated from the previous layer with the PF of each link and feed them into the network for prediction. LT represents the link prediction of the T stage, referred to as PAF in the paper, which is a set of two-dimensional unit vectors representing connecting to two key points. Phi represents the CL architecture responsible for generating this vector. Similarly, the architecture of the first stage differs from the subsequent stage but is analogous to the key point architecture, and hence it is not reiterated here. Let's refer to the following image. Figure 3 illustrates the picture map generated by the first, third, and sixth stages. The top row in figure 3 represents the confidence map for the right race, while the bottom row represents the PF for the right upper arm. It can be observed that in complex background with multiple people, through multiple adjustments, the position of arm and wrist, which might have been initially misjudged, are gradually correct in both key point and PF. The architecture of lightweight open port is as shown in Table 5, where the backbone utilizes dilated mobile net V1 with the original VGG convolutions 4.3 and 4.4 appended to the backbone. Additionally, the architecture of 4.3 convolution 4.3 is modified to use stepwise convolution to reduce computational load. In the additional stage, a shared 3x3 convolution layer is employed, while the refinement stage only utilizes one layer. Furthermore, the original 7x7 convolution is replaced with a 3-layer 3x3 structure to reduce the number of parameters. After several stages of parameter and computational reduction, the comparison result with the original open host are shown in figure 4. AOC refers to the GPU Iris Pro Graphics P280, while CPU denotes the 6-core IT. It can be observed that regardless of the device used, the original model of OpenBook achieved approximately 1 FPS on these two devices. In contrast, the improved model achieved computation speed of over 25 FPS on both devices. In this flowchart, I will first input RGB image into OpenPort. Then I will perform data preprocessing. After that, I will use the OpenPort model to extract key points. Once the key points are obtained, I will normalize and set them. Next, I will use the set key point as input. They will then pass through a multi-layer perceptron for classification, completing the task of post recognition. The affinity score generated between PF and candidate link vectors must exceed a minimum PF score threshold in order to be retained. Lowering the threshold for the affinity score aims to preserve more key points. The dataset was initially encoded into VGR image using OpenCV. However, many key points couldn't be detected. Therefore, I transferred the image channels to RGB. It's noticeable that the number of detected key points has increased significantly. The first step for the posture recognition is feature extract. The box may contain up to 18 key points. The key point contain the facial part, neck, shoulders, arm and neck, and the order of the key points are mentioned on figure 5. First, I will select the feature that contains all 18 key points. After that, I will normalize the key points and then save them as a MPY file. Multi-layer perception is a basic structure of artificial neural network consisting of multiple layers of neurons, with each neuron in one layer connected to every neuron in the next layer. In NLP, each neuron is connected to every neuron in the previous layer, but not to other neurons in the same layers. My structure of NLP includes an input layer, two hidden layers, and an output layer. Data passes through the neurons of NLP in a feed-forward manner, from the input layer through the hidden layer to reach the output layer. Neurons in each layer receive input from neurons in the previous layer, and these inputs are weight and sum before being transformed by an activation function to produce the input for neurons in the next layer. My input layer is 36 because of the coordinates of 18 key points, and then the two hidden layers are respectively 128 and 64 neurons from the input layer through the hidden layer. Both of them use ReLU or activation function. Next, during the training of NLP, the progression algorithm is typically used to adjust weights between neurons in order to minimize the model loss function. Propagation adjusts weights by computing gradient to make the model's prediction closer to the actual value. I use cost entropy for loss function and Adam for optimizer. Lastly, my output is 5 kind of pulse, and the activation function of the output layer is softmax function. It is used for multi-class classification problem. The training data set is collected in one lobby, and we collect 5 pulses of data, which is sit, fall, kneel, stand, and squat. I will train them into the MLB network, and I will get a training model. I separate 80% of data into training data and 20% of data into validation data. Both of their training accuracy have reached to 98%. I will demo 3 pulses from the test data later, and my test data sets are collected in CA time. The model will predict the pulse in the video and demonstrate the confidence score as well. And this is the demo of sleep. And this is the demo of squat. Experiment results consolidate the proposition can achieve good accuracy in posture recognition, and its lightweight architecture is feasible in real-time computation for further hardware implementation. Thank you for your time and attention.
PF is implemented in this research?
Okay. PF represents the link prediction, which is a set of two-dimensional unit vectors representing vectors connecting to two key points.
Can you can you can you explain equation in page 5?
ST represents the covenant map predict for each key point in the T stage, and rho denotes the shear architecture of the T stage.
Can you go to your accuracy plots? Before. Yeah. Why does the loss for the validation start at 120%?
Can you say again?
Why does the validation loss start at 1.2? Anyway, another question is same as your friend. You should compare to someone or the state of the art. I don't think you're the first one to make this, and you should compare to state of the art. It's not really a question, but yeah.
听了。
哦，没有，我没有跟别人比较的结果。哦，你不是第一个做这个东西的吧？
I haven't done the comparison with another method yet.
If I'm not mistaken, you haven't yet published a paper, right?
Right.
You have any the conference paper published?
You mean which friend?
Conference paper.